For lecture 3, we're going to talk about orbitals, hybridization, and geometries. This is from chapter 2 in Wade, and the point of this lecture is basically to establish the origins of bonding in organic molecules and also the origin of molecular shape, which, as we'll see in the coming chapters, plays a critical role in determining the behavior of a molecule, whether it is in terms of physical properties, chemical properties, or reactivity. So you'll recall from lecture 1 that there were 5 basic overarching themes that I wanted to make you aware of so that when we see them coming up again and again and again in lecture, you can kind of tie everything together. We spent the last couple lectures talking about things like resonance and how electronegativity affects things like major contributors, minor contributors in resonance structures. And today we're going to talk about orbitals. It's kind of going to be the focus of orbitals. So like we said here, orbitals, the reason we want to know about orbitals is because if we're mindful of them, if we are aware of them, we can use them and their location and their density and their shape, etc., to understand bonding, determine molecular geometry, and from that predict reactivity. So let's talk a little bit about the wave properties of orbitals. In general chemistry, hopefully you learned and remember that all matter can behave like waves, and waves can behave like particles. This is called the wave-particle duality. So for a lot of the material in this chapter, it might be useful to think about an orbital as a wave. Rather than being an electron behaving like a particle, let's think about an electron behaving like a wave. So the picture up here that we have of an atom, kind of an old-fashioned picture of the atom, this is called the planetary model. The idea was that the atom consisted of a nucleus in the center, kind of like the sun, and the electrons orbited around the nucleus the same way that the planets revolved around the sun. In a lot of ways, this planetary model of the atom explains a lot of observations like energy levels and transitions between those energy levels, can satisfy our intuition because it's a very visual, kind of physical representation of something that is, in a lot of ways, very abstract. But it is ultimately incorrect. We now know, in terms of modern chemistry, that the atom is a lot more sophisticated than this very simple picture. Rather than thinking about electrons as being these little discrete particles that revolve around the nucleus in these fixed set kind of regular patterns, what we might call orbits, it's more realistic to visualize electrons as residing in some three-dimensional region of space. And instead of calling these orbits, we call them orbitals. And these three-dimensional regions in space in which you can find electrons are defined by what we call a wave function. It's basically a very nasty mathematical equation that describes as much about the orbital as we can possibly kind of build into one equation. The mathematical symbol that we give the wave function is psi. So if you see that at some point, that's all that it's referring to. If you see psi, it's just referring to a wave function. Now, each orbital in an atom has a unique wave function associated with it that describes it mathematically. An s orbital has a wave function associated with it. A p orbital has a wave function associated with it. A d orbital, etc. These orbitals, again, rather than thinking about the electron as being a discrete particle, we want to think about the location of the electron as being a probability, these orbitals being probability based. And it turns out that if we square the wave function, it tells us the probability of finding an electron with some energy in a given region in space around the nucleus. So if we were to say simulate an s orbital a spherical orbital that has an electron moving around it, moving through it at some probability. If we were to take a snapshot once every second or once every millisecond for some period of time, and we were to overlay where the electron was at each snapshot into one picture, we might get something that looks like this right here, where we've got a little dot for every snapshot where we found an electron. So you'll notice that for an s orbital, most of the time we find that electron towards the nucleus, kind of centered around the nucleus, as close to the nucleus as it can realistically get. And as we look farther out from the nucleus, we are discovering electrons, or discovering the single electron, at a lower probability. So again, these you can think about as being a probability density. How dense is that orbital in terms of finding that electron? Now again, just to be clear, when I say density, I don't mean where are there the most electrons and where are there fewer electrons, because in an s orbital, there can only be up to 2 electrons at any given time. So the real density is only going to be up to 2 electrons, but the probability of finding them those electrons at some position within that orbital, we can think of as being a probability density. Orbitals that we know, 1s, 2s, 2p, 3s, 3d, etc., those are wave functions. Those orbitals are described by a wave function. So just recall that the 1s and 2s orbitals, those are spherical. The s means spherical, or represents a spherical orbital. And the p, for example, a 2p, is a barbell-shaped orbital. So these have directionality. A spherical orbital essentially has no directionality, or in other words, infinite directionality. No matter how you rotate that orbital, it's going to look the same. But a barbell orbital, like a p orbital, like we see here, does have directionality. So it might be oriented in the x direction, in which case there's no electron density in the y direction or the z direction. This plot right here is the electron density, essentially the probability of finding an electron, plotted as a function of the distance from the nucleus. So as we say, start at the nucleus, there's as close to the nucleus as we can get anyway, we should have nearly infinite electron density. That the electron is going to spend as much time as it can around that, as close to the nucleus as it can get. And as we go out, as we increase our distance from the nucleus in any direction, either left or right, the probability drops off. This is in an inverse relationship, which is what you'd expect for a spherical orbital. The plus and minus sign here represents the mathematical sign of the wave. Remember that an electron is behaving like a wave, so we can imagine the orbital in which you find that electron as basically being a 3-dimensional wave. So this just means is the wave in the positive phase or the negative phase. This isn't to say this is low probability or high probability. This is just representing a mathematical sign. Now, for a p orbital, that density looks a little bit different. You'll notice that for a p orbital, at the nucleus, there's basically no probability density. Most of the probability density in a p orbital lies farther away from the nucleus. So that's represented here in this graph, that as we look at the nucleus, there's no probability of finding an electron there. And as we move out, that probability increases and then will eventually taper off as we reach the outer reaches of those orbitals. And again, we have a positive phase of the wave and a negative phase of the wave. But where the region in space where there is no probability of finding an electron is called a node. And if it's a 2-dimensional node, you'd call it a nodal plane. The s orbital doesn't really have any node. It has something that we call an antinode, because we approach infinite probability at the nucleus, but of course there can't literally be any electrons at the nucleus. So we call that an antinode. But regardless, a node is where you would find zero probability of having an electron. One fundamental feature of orbitals is that they can be mixed. And because orbitals can be viewed as waves, when they mix in the same way that waves would mix. So when we create orbitals by mixing them, we do so by taking what is called a linear combination. And the term that chemists use for this is LCAO, the linear combination of atomic orbitals. So just to take a step back to set us up here, atomic orbitals, when we talk about atomic orbitals, what we mean are the orbitals that exist in non-bonded atoms. So if we're looking on a single atom, a 1s or a 2s or a 2p orbital would be atomic orbitals. Now, when we mix two orbitals or overlap them from the same atom, we mix them and we're going to call those hybrid orbitals. You may have learned about those in general chemistry. We're going to spend some time today talking about those. Hybrid orbitals that you may have learned about, like sp2 and sp3, those are formed by mixing atomic orbitals on the same atom. If we mix two or more orbitals on different atoms, on separate atoms, so one carbon to another carbon, for example, we call those molecular orbitals, and that is where we make bonds. So again, mixing orbitals from one atom with another atom, if we overlap them, that's where bonds come from. And again, we're going to spend more time talking about that today. Those orbitals can either be regular atomic orbitals, for example, mixing a 1s on a hydrogen with a 1s on another hydrogen. They can also be hybrid orbitals. So if we're going to mix, say, an sp3 from one carbon with an sp2 from another carbon, or an sp3 from a carbon with a 1s from a hydrogen. You can mix hybrids with hybrids, you can mix atomics with atomics, and you can mix atomics with hybrids. As long as they are on separate atoms, we're going to refer to them as molecular orbitals. So what do I mean by linear combination? Well, if we are going to mix two orbitals, the rule in chemistry is that we will also create two new orbitals. So the analogy I like to use is, say, mixing a glass of water with a glass of orange juice. If you mix a glass of water with a glass of orange juice, in real life, you'll end up with one big glass, which is 50-50 water and orange juice. That's not how orbitals behave in chemistry. When we mix two orbitals in chemistry, we produce two orbitals, and both of those orbitals are the mixture. So the analogy back to water and orange juice would be that if we mix a glass of water and a glass of orange juice together, we will end up with two separate glasses, two distinct glasses, and both glasses will be 50% water, 50% orange juice. So it's kind of like we're going to mix everything together and we're going to pour it back out into the original containers. So when you do that, the way that we get two orbitals is by taking a linear combination. So let's say that we're going to mix a 1s on a blue atom with a 1s on a red atom. So if we're mixing two orbitals, we should produce two new orbitals. So those two orbitals that we're going to get are going to be the result of adding the two waves together or subtracting the waves together. Mixing these waves in these new fashion creates a new wave function, and that wave function, or those wave functions that we produce, those new orbitals, are the linear combination. So adding the two waves or subtracting the two waves. Now, when we add the waves together, we call that a bonding orbital, and usually that's going to be a sigma bond. This Greek letter is sigma right here. And so this would be a sigma 1s molecular orbital, mixing two orbitals from separate atoms. This would be the bonding orbital you get from adding the two waves together. If you subtract the two waves together, we're going to get something called an antibonding orbital, and that is a sigma. We would represent that as a sigma star molecular orbital. So what do I mean by mixing orbitals, or what do we mean by adding orbitals or subtracting the orbitals in this way? Well, let's look at what it looks like to add two orbitals together. Again, mixing these orbitals in such a way that we add them. So think about waves. If you have two waves that are in the same phase, meaning that both waves are going up at the same time. In the positive phase, let's say both waves are going down at the same time. In the negative phase, they're moving together. Okay. We say those waves are in the same phase. If you do that to two waves, whether they are sound waves or physical waves, like waves in water, for example, the result is that you would get a single wave that is amplified. Mixing two waves in the same phase amplifies the wave where those two things mix. So if we're going to take two orbitals and add them together, say add them in the same phase, here's a 1s orbital from, say, the blue atom, here's a 1s orbital from the red atom. We're going to overlap them, move them together and overlap them. And since these two waves are mixing right here where they overlap, and since those two waves are in phase, they're going to amplify. So now we have a region in space between the two nuclei, this region right here between the two nuclei, where we have increased the probability of finding an electron. Now that means that we formed a bond. Whereas if they were separate, there's no probability of finding electrons between them. And as we bring them together and their orbitals mix, their waves mix, you increase the probability of finding an electron between the two atoms, between the two nuclei, and that is a bond. By definition, when you have two electrons being shared in a region of space between the two nuclei, that's a bond. And again, we would call this sigma. This is a sigma bond, a sigma bonding orbital. So the opposite of that must be true if we subtract the two waves. The analogy to subtracting the two waves is to mix them out of phase. If you have two waves that are out of phase, so one is up while the other one is down, and one of them is down while the other one is up, and you mix them, the result is what we call destructive interference. The two waves essentially cancel each other out. This is also how noise-canceling headphones work. So in an orbital, or in an atom, or a molecule, where we are mixing two waves out of phase, the region in space between the two nuclei, where the waves overlap out of phase, results in destruction of the wave. We have zero probability. The wave does not exist between the two atoms anymore, between the two nuclei. That is what we would call a node. And the result looks like this, whereas before we had increased density between the nuclei, now we have no density between the nuclei. You can't make a bond out of that orbital. If you put electrons in that orbital, they are not allowed to exist between the two nuclei. Therefore, you cannot get a bond from using those orbitals. That's why we call this a antibonding orbital, a sigma star. The star just indicates an antibond. I've got an image from another book. This is basically representing the same thing. If we take two wave functions that are in phase, if they're not overlapping, there's no bond. There's no electron density between them. But when we bring them together and overlap them, you increase that probability, you amplify the wave, and now you have a bond. We might call that constructive interference or just amplification of the wave. If we mix them out of phase, where they overlap, you're going to have zero probability. Here we have high probability for the bond. Here we have zero probability for the antibond. That's destructive interference, as we would call a node. This is just the density, again, size squared, the wave function squared, looks like this. We have high probability on the opposite sides of the nuclei, but zero probability between the two. Over here, we have high probability between the two. So why does this happen? Why does mixing orbitals in two ways, constructively and destructively, generate bonding or antibonding? Because we're mixing two orbitals and we have to follow the law of conservation of energy, the two new orbitals that we create need to have the same energy in a combined sense as the two orbitals that we started with. So this is a diagram of kind of a before and after picture. This is called a molecular orbital diagram. It's basically a before and after picture, where on the outside, we have the before picture, a simple atomic 1s orbital, spherical, not mixed with anything, from one atom. And here we have another 1s atomic orbital, spherical, not mixed with anything, from another atom. And then in the middle here is the result when we bring them together. So when we mix these two orbitals, two things happen. We can either mix them constructively, which we saw give us a bonding orbital where we amplified the wave between the nuclei, or we can get an antibonding orbital where we basically neutralize the wave between the nuclei. Now, as you see here, this is a plot of energy. So it turns out that the molecular orbital, in the bonding sense, is, first of all, lower in energy than the original atomic orbitals were, and the antibonding orbital is higher in energy than everything. So imagine that this were a hydrogen, and this was a hydrogen. Each hydrogen would, say, bring one electron. So when we mix the two orbitals, we get two electrons to place into those two orbitals. And if we follow Aufbau principle and Hund's rule, we should have both of those electrons going into the bonding orbital. Lowest energy orbitals get filled first, then higher energy orbitals get filled later. So the result of mixing these orbitals, the result of mixing these 1s orbitals together, is that the electrons that were in them individually, now both of them get to go down in energy. Bonding is a fundamentally stable process. The result of mixing these orbitals should allow the electrons to go down. If for some reason it was the case that mixing the orbitals forced the electrons to go into a higher energy state, then the orbitals simply wouldn't mix and we wouldn't have bonding. The reason that molecules form, the reason that we make bonds between atoms and we get molecules that form and reactions that occur to make new bonds and maybe break less stable bonds, is that bonding lowers the energy of the electrons. Now, like I said, I referenced the law of conservation of energy. I said that the sum of the energy of the original orbitals needs to equal the sum of the energies of the new orbitals. So the two orbitals at some energy mix to yield two new orbitals. One will be at some margin of energy lower, so the bonding orbital will be some degree lower in energy, and the antibonding orbital will be at some degree higher energy. That way, the total amount of energy that we start with, let's say we have 1 unit of energy here, 1 unit of energy here, we have 0 energy here, lower, and 2 energy here, higher. So we have 2 units of energy to begin with and 2 units of energy when we're done. But the result is that both of the electrons now get to reside in the mixed orbital, where the electron density is increased between the two nuclei and also at a lower energy. This plays an important role in reactivity. This is a very simplified energy diagram. This is something that you might see if you were to mix an s orbital and a p orbital together in the same molecule. Again, this is a very, very simplified picture. But let's say we have a one electron in an S, one electron in an S, and one electron in a P, and one electron in a P. So we have 4 electrons that we're going to mix. Notice that when the S's mix, we get the sigma very low, and we get the sigma star very high. Mixing these S's gives us a very, very, very stable orbital and a very, very unstable orbital. Mixing the P's gets us a somewhat different picture. Now, we still get a bonding orbital that is lower in energy and a antibonding orbital that is higher energy. By the way, we call these pi orbitals because they are coming from P's instead of sigmas, which are coming from S's. But you'll notice that because the pi doesn't go down in energy quite as much as the sigma, the pi star doesn't go as high up in energy as the sigma. So out of these 4 electrons that mix, the S's are going to get to go down far in energy, and the P's are going to get to go down a little bit in energy. This is important because it tells us how this molecule might react. If we were to have this molecule act as a Lewis acid, if it were to accept electrons, we would put the electrons into something that we call the LUMO, the lowest unoccupied molecular orbital. Where are those electrons going to go? Well, they're going to go into the lowest energy orbital that has available space for electrons. So if this molecule acts as a Lewis acid, we can easily predict that those electrons will populate a pi star, a pi antibonding orbital. And you might remember from general chemistry that when you populate an antibonding orbital, you end up weakening the corresponding bond. So if this molecule acts as a Lewis acid, the electrons will go into the pi star and we will disrupt the pi bond. On the other hand, if this molecule acts as a Lewis base, the electrons that we're going to donate are going to be the highest energy electrons. Again, if this molecule has a choice to give up its pi electrons or its sigma electrons, it's going to give up the pi electrons because they are higher in energy. We call that the HOMO, the highest occupied molecular orbital. And so we can predict that if this molecule acts as a Lewis base, it's going to be using the pi bond as the source of the electrons that it's going to donate and not the sigma bond. So again, understanding this relative energy level and the idea of populating orbitals from low to high, like we learned in general chemistry, helps us predict what bonds might break in a molecule or what bonds might be more likely to form in a molecule if it's going to react in some way. We'll talk more about HOMO and LUMO in future chapters. So there are other ways that orbitals can mix. We've talked about so far mixing S's with S's and P's with P's. Let's look at some other ways that orbitals can mix. If we take 2 p orbitals and we overlap them end on end, we're going to overlap this end of the p orbital with this end of the p orbital. And notice that we're going to mix the lobes that are in phase. So we have a positive phase and a positive phase. Where those lobes of the orbitals overlap, we should get increased electron density between the nuclei. Indeed, we have that. So this is going to be a bonding orbital, again, because they are in phase, but we call it sigma. Why do we call it sigma if we're mixing p's? Well, sigma really means end-on-end overlap. It doesn't really mean that it comes from s's, although s's do overlap in that end-on-end fashion. But sigma means overlapping end-on-end. So we can actually get a sigma bond from a p orbital, a pair of p orbitals, as long as we're overlapping them end on end. So that would be a sigma bond. We can also overlap them out of phase, the positive lobe with the negative lobe. Again, that's end on end overlap. It's just that it's now interference. So we would call that sigma star. We can overlap a p with an s. In phase, we're going to get a bonding orbital. Again, it's end on end. So we're going to call it sigma and it's bonding. And again, notice that The region in space where they are in phase, positive with positive, is amplified, and where it's out of phase, positive with negative, is destroyed. We can get end-on-end destruction, again, overlapping the plus with a minus phase, for example. Where those regions overlap, we're going to get an antibonding orbital. And where they are in phase, we're going to get amplification of that. All of these are sigma bonds or sigma antibonds, though, because they all are going one end of one orbital to the other end of another orbital. It's end on end. But if we have p orbitals, we can also have side-to-side overlap. And that is where we get the pi bond. So side-to-side overlap in phase, where the positive lobes are mixing and the negative lobes are mixing. We get increased density between the nuclei here and here. That side-to-side overlap is called a pi bond. That's pi overlap. If we have side-to-side interference, where we're going to overlap things out of phase, positive with negative and negative with positive, we get that node. Again, those waves are going to interfere. They're going to give us 0 probability, and that we would call a pi star. So again, end on end gives us sigma, side to side gives us pi. Antibonding is notated with the star. So let's talk a little bit about some problems with the simpler bonding theory called valence bond theory. A couple lectures ago, we talked about Lewis structures and valence bond theory. The idea simply that atoms will overlap their valence orbitals, their valence electrons, and pair up those electrons to make bonds. We use that method to draw Lewis structures and figure out what the connectivity and shape is going to be for molecules. That's all part of a simpler theory called valence bond theory. And I want to show you some problems with valence bond theory. So let's look at carbon. Here is the electron configuration for carbon. It's 1s2, 2s2, 2p2. So it would look something like this. The low 1s would be filled, higher 2s would be filled, and the 2p orbitals, we would have 2 electrons in 2p orbitals. Those would be following Hund's rule, of course. Now, if we know that carbon makes 4 bonds, there's all kinds of examples where we can show carbon making 4 bonds. And we understand from valence bond theory that carbon should make bonds by pairing up unpaired electrons. We cannot explain where carbon's bonds come from. It's only got 2 unpaired electrons. So based simply on this electron configuration, we have a really hard time explaining carbon making 4 bonds if we simply follow valence bond theory. There's a way to fix this. Once scientists kind of realized that, hey, we've got a problem here, one solution to that problem was to suggest that maybe when carbon makes 4 bonds, what it's actually doing is moving an electron from the 2s up into the 2p. So we're taking one of our electrons that are paired up in the 2s, and we're going to unpair it, and we're going to put it in its own orbital in the 2p. Now, in doing so, we get something called an excited state. This is a configuration of the electrons that is higher in energy than it needs to be. But in this excited state, carbon could theoretically now make 4 bonds according to valence bond theory. We have 4 unpaired electrons, and so we could pair up those electrons with electrons from other atoms and make 4 bonds in doing so. But again, there's a problem. Okay? The first problem is the energy. These 4 bonds would be different. We would have 3 bonds that are higher in energy coming from the p's, and we'd have 1 bond that's lower in energy coming from the s. Now, in a molecule like methane, CH4, we have experimental evidence that shows that all 4 of the carbon-hydrogen bonds are equal in energy. And if you think about it, there's really no reason to expect that one of the carbon-hydrogen bonds should be low in energy and three of the carbon-hydrogen bonds should be higher in energy. That doesn't really make sense. There's no reason why nature would selectively make one of these types of bonds low in energy and three of those types of bonds high in energy. It just doesn't make sense. Furthermore, let's think about the geometry. Remember the geometry of the p orbitals from the other day. They look like this. Those p orbitals, 1, 2, 3, are in the x, y, and z coordinates. So if we're going to be making three bonds with the three orbitals, the three p orbitals, those three bonds should be at 90 degrees from one another. We know that's not the case. Furthermore, that s orbital is infinitely directional. So if we put that s orbital in there and say, okay, we're going to be making one bond with our s and three bonds with our p's, we should have three bonds at 90 and one bond at some other angle. That's not reality. In reality, according to Vesper theory, like we've seen before, 4 electron domains around a nucleus should be 109.5 degree bond angles. So we have a problem. Valence bond theory fails to explain how we can possibly have 4 identical bonds in energy and how we should have 4 identical bonds all at 109.5 degrees from each other. It doesn't work simply using valence bond theory. So the way that we can explain this is with a somewhat more sophisticated theory called hybridization theory. You may have learned about hybridization theory in general chemistry. I'm going to go over it fairly briefly here so that you are reacquainted with it. The idea with hybridization theory is that we're going to mix these orbitals together before actually bonding. So instead of bonding with a px, a py, a pz, and an s, we're first going to mix them. Instead of bonding with the atomic orbitals, we're going to mix with hybrid orbitals. So there are basically 3 ways that the s and the p's can mix. The first way is to mix the s with one of the p orbitals, let's say the px, and we're going to leave the other 2 p orbitals, the py and the pz, we're going to leave them unhybridized for the time being. This is what happens when we need to make bonds with 2 other entities. So remember what we do when we mix 2 orbitals, we should produce 2 new orbitals that are the kind of mixture of the 2, hybrids of the 2. We call those hybrids sp hybrids because we're mixing an s with a p. Notice also that the energy of these hybrids is exactly 50% of the way between the energy of the components from which they were made. The s orbital has low energy, the p orbital has high energy. So if these orbitals are 50-50 s and p, their energy should also be half of the way between the s and the p. We say these orbitals have 50% s character. If we look at a visual description of these orbitals, rather than an energetic description of these orbitals, we can imagine overlapping an s, let's say in the positive phase, with a p. Now, remember that where the s and the p overlap, constructively, we should get amplification of that wave. And where they overlap destructively out of phase, we should get destruction of that wave. So we get one sp hybrid that looks like this. Notice that towards the right side of the nucleus, we have enhancement of the orbital. We can also mix them in a different way. We can overlap them, let's say the s in the positive phase, with the p in the opposite phase. So instead of the positive on the right and the negative on the left, we have the positive on the left and the negative on the right. So now instead of getting amplification on the right side of the orbital like we did, the right side of the nucleus like we did in the first case, we're going to get amplification of the orbital on the left side in this case. These are our two sp hybrids. They are identical, but they have a different electron distribution around the nucleus. One of them is on the right side, one of them is on the left side. If we overlap them on the same orbital, so imagine, on the same nucleus. Remember, these are hybrids being created by mixing two orbitals on the same atom. If we overlap them together, we can see that one of the orbitals goes this way and one of the orbitals goes that way. If we make bonds with them, those bonds will be at 180 degrees. That is a linear molecule, a linear geometry. And it follows that the reason that we would get 180 degrees must be because we are using sp hybrids. Those hybrids sit at 180 degrees from one another. Okay, let's keep going. Instead of mixing the S with one P, we're going to mix an S with two P's. So now instead of having our directionality from the P in the X coordinate, we're also going to have directionality from the P in the Y coordinate. So this should not be linear anymore. We're not only going in the X direction, we're now also incorporating the Y coordinate. As far as energy goes, you'll notice that these hybrids are a little bit higher in energy because we have two p orbitals and only one s orbital coming here. This should be 33% s character and 66% p character. And so the orbital should sit at a little bit higher energy. We call these sp2 or sp squared. Some people call them sp squared. I call them sp2. You can call them whatever you want. Now, the same mode of mixing also applies here. We're going to mix an S with the px, but also with the py. So the region where the S overlaps with the in-phase lobe, we're going to get an enhanced lobe there, there, and there. And where they overlap out of phase, plus and minus, we're going to get a destructive interfered with lobe there, there, and there. Now, again, we've got contribution in one axis and another axis, giving us three hybrids. It follows that those hybrids should then be at 120 degrees. We have 360 contribution from the S, and then 90 degrees from one and 90 degrees from the other. The result of that is three orbitals, the three hybrids, at 120 degrees from one another in this case, the XY plane. Now, you'll see here that we also, of course, have that unhybridized PZ orbital that's still there. So if you were to incorporate that into the picture, it would be perpendicular to the plane in which our hybrids sit. Our hybrids are going to sit in the X and Y plane because they come from the X and Y p orbitals. But then we've still got this unmixed p orbital that's sitting in the Z. This is how we get 120 degree bond angles. For example, BH3, borane, has 120 degree bond angles. The reason it has 120 degree bond angles, the reason that VSEPR geometry exists, is because the bonds are being made with sp2 hybrids, not with sp hybrids, not with pure S's, and not with pure P's, but with sp2 hybrids. We can go one step further. If we're going to mix the S with all three p orbitals, we should get 4 equal orbitals, which would have 25% S character and 75% P character. We're going to call those sp3s. And again, if you follow that same pattern, mixing the S with a P in the X, a P in the Y, and the P in the Z, the result is 109.5 degrees. 4 hybrids that are sitting at 109.5 degrees from one another. There are no unhybridized p orbitals left. And notice that these hybrids are all equal in energy. This is where we get 4 bonds to carbon at 109.5 degrees and all 4 bonds equal in energy. We can't explain that bonding unless we incorporate hybridization theory into our picture. Valence bond theory was too simple. Remember, this is a tetrahedral shape. This is where we get the tetrahedral shape of carbon. To line these up next to each other, hopefully you'll see what's going on here. Remember that sp hybrids are made from mixing one S and one P. We would say that's 50% S character. Okay? Those orbitals are lying right 50% of the way between where the S and the P were in terms of energy. As we incorporate an additional p orbital, our S character goes down and our Y character goes up. Excuse me, our P character goes up. So we're going to have slightly higher energy. I tried to make these sp2s a little bit higher in energy than the sps were. Furthermore, if we incorporate that last pz orbital, we now have 25% S character, 75% P character. So our orbitals should have higher energy again. If you're wondering why P orbitals raise the energy of the system, I'll go back to this slide real quick and remind you that the S orbital allows us to have very, very high density near the nucleus. The S orbital allows the electrons to sit very close to the nucleus. In the P orbital, the electrons have to sit farther away from the nucleus. That is a less energetically ideal arrangement. So by incorporating fewer p orbitals into the picture, our hybrids have a lower energy. More S character means lower energy. The electrons get to sit closer to the nucleus. One thing that I haven't mentioned so far is that an atom will only mix as many orbitals together, and therefore it will only make as many hybrids as it needs to make bonds with any given number of entities. So if we have 2 entities to which we need to make a bond, we're only going to make 2 hybrids. That way those hybrids get to maximize their S character. If we have 3 entities with which we need to bond, we're going to make 3 hybrids so that those hybrids can have 33% S character. That's as much S character as you can have to give us 3 hybrids. And if we have 4 entities with which we need to bond, we're going to need to mix all 4 of these orbitals to make 4 hybrids. So the idea is that if we only need to make bonds to 2 things, there's no reason to mix all 4 of our orbitals, because the resulting orbitals will be higher in energy than they would be if we had only mixed 1p. We want to maximize our S character. Since drawing tetrahedra, three-dimensional structures, requires a little bit of visualization, I want to take some time to give you a sense of what these molecules look like in 3D. You get so used to looking at these things in 2 dimensions, drawing them as flat molecules on a piece of paper, that it's easy to overlook what these things really look like in 3 dimensions. So, in terms of drawing them on paper, chemists have developed a shorthand notation to kind of simplify the visualization of these 3-dimensional structures, to make drawing a 3D structure a little bit more simple. You don't have to be an artist to draw 3D structures to give molecules perspective like this. What we do instead is we used dashed lines to indicate that bonds go backwards or away from the reader, basically into the screen or into the board. So this dashed line here means that hydrogen is going behind the molecule. That hydrogen is represented right here. If these 2 carbons are sitting in the plane of the board or flat in your screen, this hydrogen here is going backwards. Hopefully you can see that. This hydrogen here is going forwards, coming out at us. So we're going to use a wedge-shaped bond to depict that bond comes forward towards us. And then straight lines, regular plain lines, like hydrogen to this carbon to this carbon, and this carbon to this hydrogen, mean that the bonds are actually in the plane of the board. So this molecule is called ethane. It's C2H6. And if you look carefully, hopefully you can see that this is really just 2 tetrahedra that are joined together. Each carbon has 4 entities bound to it: hydrogen, 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 and the other carbon. 4 entities bound to one another means that they should be making bonds with 4 sp3 hybrids. So those hybrids should be at 1 or 9.5 degrees from one another, which is tetrahedron. So we've got one tetrahedron around this carbon and another tetrahedron around this carbon. And because those carbons are connected, they kind of share one of those tetrahedral vertices. So on paper, you might draw it like this. Or if you have a computer simulation to kind of model these things, they look like this. If you were to represent it in a space-filling model where the carbons are bigger and the hydrogens are smaller, they look kind of like this. I have a demo I want to show you. This is methane. Again, this is a tetrahedron, and I've got it in a little chemical visualization program. So hopefully you can kind of see what a tetrahedron looks like as I spin it around in 3 dimensions. The simplest way to view it, it kind of looks like a tripod with a single thing coming out of the top, okay? Like a 3-footed base, a 3-footed pyramid almost, with a single thing coming out of the top. That's what a tetrahedron looks like. And as you spin it around, it looks the same. It looks symmetrical on all sides. That's, again, what we understand from carbon is that it has 4 identical bonds. And these bonds should be symmetrical on all sides. Another way we can view it, let me see if I can find it here. If I put the molecule like this, like that right there, you can hopefully see that the hydrogen on the left and the hydrogen on the right are in the plane of the board. 2 of the bonds, or you can think of it as being 3 of the atoms, atom, 3 of these atoms are flat. They're in the plane of the board. They're kind of at that bent shape because it's got to be 1 or 9.5, but they're in the plane of the board. The other 2 atoms are coming out of the board. One of them is coming out of the board, and one of them is going into the board. Okay? That is how you can view a tetrahedron. So if we go back to our picture, on each tetrahedron, one atom is in the plane, another atom is in the plane. So we have two atoms in the plane. One of them is coming out, one of them is going away. That's what we have here. Two atoms in the plane, one coming out, one going in. I'm going to switch. This is ethane. Here. Again, now we have two tetrahedra that are stuck together. Again, you can see that this hydrogen here is in the same plane as this carbon and that carbon. Okay, these three atoms are in the plane on this tetrahedron on the left. We've then got one atom coming out and one electron going away. We've got the same thing going on the other atom, on the other carbon. This hydrogen is in the plane with that carbon and that carbon, and then we've got one hydrogen coming up, out at us, and one hydrogen going back away from us. If I turn this kind of end on end like that, you can also see that these atoms are staggered. Okay. The atoms on the front carbon are staggered with the atoms on the back carbon. That maximizes their distance from each other. That minimizes their repulsion. That's one way that ethane can exist, is having those atoms be staggered. But because these bonds are cylindrical, no matter how they rotate, they still maximize their overlap. You can rotate this bond, which means that we could actually rotate these atoms so that they end up being eclipsed with each other. I'm going to do that right here. So now I've rotated them. I've rotated that bond. And so now we have the atoms on the front carbon, these three hydrogens on the front carbon, eclipsed with the hydrogen on the back carbon. So again, that's called eclipsed ethane, like that. This is called staggered ethane, like that. And because this bond is freely rotatable, it's the same molecule. Ethane is ethane is ethane. It's just that as this bond rotates, we get staggered, then eclipsed, then staggered, then eclipsed. I'm going to switch to my whiteboard here, and I want to talk about multiple bonds for a moment. So far, we've only been talking about single bonds. So I want to talk about how double bonds form. Let's look at a molecule like this. Carbon double bonded to a carbon, and then we'll just give it hydrogens like that. Let's use what we know about hybridization theory and molecular orbital theory to figure out what types of bonds these are, or how these bonds are being formed in the first place. Now, let's first think about what the hybridization must be. Remember that the hybridization that an atom adopts is based on the number of entities that it needs to bind to. If it's got 2 entities, it's going to be sp. 3 entities is going to be sp2. And 4 entities is going to be sp3. It's going to mix as many orbitals as it needs to produce as many hybrids as it needs to bound to that number of entities. So each of these carbons is bound to 3 entities. The 2 hydrogens on one side and the carbon on the other side. So this carbon should be sp2. And this carbon is the same. It's also got 2 hydrogens and 1 carbon. So 3 entities means sp2. Remember what the sp2 picture looks like. sp2 would have the nucleus right there in the middle, and then 3 hybrids. one hybrid there, one hybrid, let's say, there, and one hybrid there. Those hybrids, I'll write in sp2. Those are our sp2 hybrids, and they are at 120 degrees from one another. There was one more piece of the picture for the sp2. Remember what it was? It was the unhybridized p orbital. In the example that we used, it was a pz. We have 3 sp2 hybrids, but we also have that unhybridized p orbital left over. That is what each of these carbons looks like as far as its electron distribution around the nucleus. So we've got 2 carbons. I'm going to copy this. I'll duplicate it. And I'm actually going to flip this over to make it a little bit easier to see. Okay, there are our carbons. Now, let's imagine that these 2 carbons are going to bond. In order for them to bond, they need to overlap their orbitals. So I'm going to take this atom and I'm going to move it towards the other atom until we get bonding. I'll leave it right there. Now, what type of bonds do we make? Now, we've got one type of overlap occurring with the sp2s. The blue orbitals here are overlapping. What type of overlap is that? Well, it's end-on-end overlap. Those 2 orbitals are overlapping end to end. So remember what we call that? We call that a sigma bond. That's sigma overlap. We also, however, if we move these close enough, we'll get overlap between the p orbitals. We'll get side-to-side overlap. Both of those p orbitals are in the z direction, in the z plane, which means that as we bring these orbitals near each other, they're going to overlap side to side. And that was the other type of overlap. That was pi overlap. So the double bond that I drew here between the 2 carbons is really a pi bond and a sigma bond. One of them is a pi bond, one of them is a sigma bond. They are fundamentally different from one another. Those 2 bonds that are connecting the 2 carbons are very different. They're different in strength, they're different in stability, and they're even equal in rotationality, we'll say, rotatability. I'll show you that in a moment. Let's finish drawing this molecule, though. We're not done. We still have to incorporate the hydrogens. So we'll go back and let's bring in hydrogen. We'll make hydrogen orange. Hydrogen, I'm always going to draw as a perfect sphere because that is a 1s. Hydrogen only really has access to its 1s orbital. So we'll bring it in. We're going to make another bond there and another bond there. And again, that's end-on-end overlap, overlapping a hybrid with a spherical orbital. That overlap is sigma type overlap. Same here. That's also sigma overlap. We can do the same on the other side. End-on-end overlap there. End-on-end overlap there. Another bond, and another bond. Sigma, sigma. So all the single bonds in this molecule are sigmas. That's a sigma, that's a sigma, that's a sigma, and that's a sigma. The double bond is a sigma and a pi. I also want to point out that the pi bond has density both above the plane of the sigma bond and below the plane of the sigma bond. Be very careful not to confuse that as being two pi bonds. Really, the top is kind of like half of the pi bond, and the bottom is the other half of the pi bond. The pi bond is actually located in two positions simultaneously. Half of it is above the plane of the sigma bond, half of it is below the plane of the sigma bond. That is what we have here. Going back to our slides, here's the molecule I drew. And compare it to the sp3, neither carbon has those four entities. So this is not going to be sp3. It only has 3 entities, so it's going to be sp2. And if we combine that sp2 picture, we get end-on-end overlap from these two hybrids. We get side-to-side overlap from the unhybridized p's. That constitutes a sigma, and then half of a pi bond above, half of a pi bond below, and then the other overlap from the hybrids in purple to the hydrogens. Those are also sigma bonds. Your Wade textbook uses this balloon picture, which I really like. It kind of shows that these orbitals kind of meld into one another. Hopefully you see the difference between the sigma type bond and the pi type bond. They're very different. Let's go back and we'll look at triple bonds now. So let's draw a molecule that is a triple bond, or that involves a triple bond. We'll use acetylene. That's H bond to C, triple bond to another carbon to a hydrogen. That's acetylene. Acetylene is the fuel that burns in a blowtorch. Acetylene torch, or blowtorch, is also called an acetylene torch. So we've got a triple bond now. So we need to, again, think about hybridization theory, think about Vesper theory, and think about where the orbitals are, how they're going to overlap, to determine how are we going to explain the geometry and the nature of these bonds. So again, let's start with the hybridization. The hybridization on the left carbon should be sp. It has 2 entities bound to it. The hydrogen on the left, the carbon on the right. 2 entities. Same thing for the other carbon. Also sp. 2 entities, the hydrogen on the right and the carbon on the left. So let's go back and think about what our sp orbital arrangement looks like. For sp, we have the nucleus in the middle, and then we have one sp orbital like that, and one sp orbital like that. So that's an sp, and that's an sp. Notice I am only drawing the lobe of the orbital that got amplified by the wave. I'm not drawing the other little tiny orbital that got destroyed when we interfered the two waves. I'm only drawing the two. But remember that we had two orbitals that were at 180 degrees from one another. That's what the SP picture looks like. Now, when we went over the SP picture, we didn't draw in the other p orbitals because it gets a little bit messy. But I want to do that here. Remember that when we made the SP hybrid, we mixed the S with the PX, for example. That means that there is also a PY unhybridized and a PZ unhybridized here. So I'm going to draw the PY and PZ. I'll do one of them just going straight up, straight down. And then we'll make one that's kind of coming out of the board at us and going away from the board from us, kind of like that. So each of the carbons should look like that. Each carbon is sp hybridized. So I'm going to copy this again. And now let's make these carbons bond. We're going to bring them together, just like I did before, until they start to mix. Okay. Now, what type of bonds are we making? We are overlapping the sp hybrids end on end. Remember, that's a sigma bond, okay? End on end overlap is sigma. It's almost always going to be that hybrids overlapping will be sigma type. They'll be end on end overlap. But we've also got the green orbitals that are parallel. We've got that side to side overlap. We've got end on end overlap from the sigma, from the hybrids. We've got side to side overlap from the p's. That's pi. And we've also got end on end from the pink. I said end on end again. That should be side to side again. So we've also got a pi there. So our triple bond between the two carbons has one end on end and two side to sides. That's a sigma and two pi's. We can bring back our hydrogens. Remember, our hydrogens were just spherical 1s's. Those overlap there and there. Also, end on end, which is sigma and sigma. So our triple bond in acetylene will be sigma, pi, and pi, and then sigma between the CH and sigma between the CH. Going back to our slides, this is the picture our book gives us. Again, this is exactly what we just drew. Here's acetylene. We have triple bonds at 180 degrees. Each carbon has two atoms attached to it, so they should be sp hybrids. We've got the two sp hybrids here in purple. We've got the py in green. Those are overlapping side to side. And the pz's in blue. Those are overlapping side to side. Just to clarify, the book by default always mixes the PX first and not the PY or not the PZ. There's no real reason it has to do the PX. It just does the X first. It's kind of irrelevant which Y or Z or X orbital does what, because they're the same. So don't stress too much about whether it's the PY, the PX, or the PZ that's mixing or forming the sigma or forming the pi. Just know that it's one P that gets mixed with the S. That leaves two P's to go side to side, make pi bonds in their unhybridized form. Okay, we're almost done. Let's look at a couple other features of sigma bonds versus pi bonds. If we take two molecules like this, let's say that have an unpaired electron in a non-bonded sp3, this is called a methyl radical. Don't worry about that yet. It's called methyl. But they've got one unpaired electron in its sp3. Over here, one unpaired electron in its sp3. If we overlap that, that's how we get ethane, by the way. This is ethane. We've seen ethane before. That's a sigma bond. We're pairing up unpaired electrons by overlapping two hybrids end on end. That is a sigma bond. It turns out that because of the geometry of end on end rotation, it doesn't matter, end on end overlap. It doesn't matter how that bond is rotated. That bond, whether we rotate the group on the left or the group on the right, no matter how that bond is rotated, it will maintain its overlap. And again, that's how we get eclipsed ethane with all the hydrogens in the plane with another hydrogen. So this hydrogen is in the plane with that hydrogen and they are overlapping, or they are eclipsing each other. Or staggered, where this hydrogen is kind of bisecting these two hydrogens over here. Just to go back to remind you, this was staggered ethane, right? They are staggered. The back hydrogen is bisecting the front. This is eclipsed ethane, where they are all lined up with one another. Those can interconvert again because you can rotate between or rotate around that sigma bond, okay? So rotation around single bonds, sigma type overlap, is allowed. This overlap is spherical or cylindrically symmetrical. So rotation in any direction will not impede bonding. That's very important because it lets us understand how floppy this molecule might be. On the other hand, pi bonds are very rigid, okay? Here's the sigma bond. We'll kind of ignore that for a moment. That bond, that single bond in and of itself is rotatable, but if we also put a pi bond above and below it, notice that in order to get side-to-side overlap, these orbitals need to be parallel. So if we try to rotate this bond, we're going to move one of those orbitals out of the plane of the other one. So now that overlap is broken. These guys can no longer overlap. They are orthogonal to one another. So double bonds do not rotate. Triple bonds do not rotate because by rotating, you would end up disrupting that pi bond. And that takes too much energy. It takes way more energy to break a bond than you get by rotating it. So you could have two different molecules here and here. For example, this is called cis-2-butene and trans-2-butene. We'll talk about cis versus trans in a little while. But notice that the connectivity is the same. You've got CH3, single bonded to C, double bonded to C, single bonded to CH3. And then we have hydrogen and hydrogen on the double bonded carbons. We have the same thing here. CH3 single bonded to C, double bonded to C, single bonded to CH3, and then we've got two hydrogens on the double bonded carbons. But you might think, well, okay, you could just rotate around that central bond to move, say, this CH3 group down here. Just rotate around that molecule. But remember, you can't do that. This double bond is really a sigma bond and a pi bond. We already saw that. So this molecule, the cis-2-butene, is a different molecule from the trans-2-butene. They have different properties. Okay? With a pi bond, overlap is planar. So rotation in any direction will break the bond. Therefore, it doesn't happen. Rotation of pi double bonds being caused by pi type overlap, is not allowed. We'll keep that in mind as we go through the coming chapters as well. The very last topic for today, I want to talk a little bit about isomerism. Isomers are different compounds with the same molecular formula. There are different types of isomerisms, different types of isomers. They differ in how they're related. But for now, we're going to look at two types of isomers. One type is called constitutional isomers, and the other type are called stereoisomers. So constitutional isomers are isomers that differ in their bonding sequence. Essentially, the atoms are connected differently. Here I have a bunch of different constitutional isomers. This guy is called cyclopentane. Again, if you're hopefully are getting comfortable with line angle structure, this is a 5-carbon ring. That's 5 carbons. If you count all the hydrogens, that's C5H10. This is called methyl cyclobutane. This is a ring of 4 carbons with a single carbon coming off of it. If you count all the hydrogens here, it's also C5H10. So cyclopentane and methyl cyclobutane have the same formula, but they are very clearly different. They have different connectivity. Basically, their constitution is different. They are constitutionally different from one another. We can also look at 1-pentene versus 2-pentene. These are also C5H10. The connectivity is different, though. You'll notice that in 1-pentene, the double bond is between the first carbon and the second carbon. And in 2-pentene, the double bond is between the second carbon and the third carbon. You're probably guessing that's what the 1 and the 2 means, and you'd be right. The 1 means that the double bond starts on carbon 1, and the 2 means that the double bond starts on carbon 2. All 4 of these structures, 1-pentene, 2-pentene, cyclopentane, and methyl cyclobutane, all have the same formula, C5H10, but they have different connectivity. This is N-butane, or sometimes it's just called butane. This is isobutane. It's also called methyl propane. They are C4H10 is their formula, but again, clearly they have different connectivity. Here's pentane or N-pentane. This is called isopentane or 2-methylbutane. This is called neopentane or 2,2-dimethylpropane. They are all C5H12. But again, clearly different connectivity. That is what a constitutional isomer is, or a constitutional isomers are two or more molecules that have different connectivity, but the same formula. The other type of isomer that we need to know for now are called stereoisomers. Stereoisomers have the same formula because they're isomers, but they also have the same connectivity, meaning they are not constitutionally different. They are actually more similar than constitutional isomers are. Rather, the way they differ is in how their atoms are oriented in space. So we just saw cis-2-butene and trans-2-butene. And I walked you through how they actually have the same connectivity. And of course, they have the same formula as well. Their connectivity is the same. Single bond, double bond, single bond between the carbons. Single bond, double bond, single bond between the carbons. The only difference is how these CH3 groups are oriented in space. In the cis molecule, the two CH3 groups are together. They are kind of on the same side of the molecule, the same side of the double bond, the top side, if you will. The trans, they are on opposite sides. If you were to draw a line right through the double bond here, right there, draw a line right through the double bond. The cis has the methyls on the same side. The trans have the methyls on the opposite side. They are different. They are oriented differently in space. So those are stereoisomers. 1-butene is also an isomer of cis-2-butene and trans-2-butene, but it is constitutionally different. The double bond is in a different position. The connectivity is different. Instead of the double bond being between carbons 2 and 3, like it is with 2-butene, it's between carbon 1 and 2 in 1-butene. So 1-butene is a constitutional isomer of trans and cis-2-butene. Cis-butene and trans-2-butene are stereoisomers of each other. Another term that is sometimes used, I am in the habit of using it. I'm not sure how much other professors might or what books you have might use this, but another term for cis and trans stereoisomers, so isomers that are stereoisomers because they are cis and trans, are also called geometric isomers. There are more terms for these that we're going to see later. We can get very, very, very specific or very, very, very general in how these things differ. But for now, constitutional isomers, remember, are same formula, different connectivity. Stereoisomers, same formula, same connectivity, but different orientation of the groups in space. You'll see over time that stereoisomers always come in pairs. That's why we use the term stereo, like left and right stereo speakers. These guys will always have a twin or kind of an evil twin, if you will. So that's it. That's the end of lecture 3. The workshop material for this chapter in the Stramanis workbook is chapter 3.